Hi everybody, welcome back to Chem 140. It is Monday of week 4, and we are moving right along the quarter. We're already a third of the way done with this class, and it's probably about time that we talk about actual chemistry. But first, some little announcements that we have. Down at the bottom, you see that quiz number 2 is due tomorrow. That's Tuesday, the 12th of October. I can barely read this on the screen. It's Tuesday. I just can't read the number. It looks like a 12 to me. Make sure you get that in as soon as possible. It closes the following day on Wednesday, and then it gets graded and released on Thursday, so you'll get your scores back then. We're going to do lab number 2. We're going to formally talk about it on Wednesday this week. But before we get started, I did want to talk about, like, how does grading work? How are labs graded and stuff? Now, all your quizzes, Canvas auto-grades them for you, and then I release all of the scores. We're going to do Unit 6. This just talks about Unit 9, so don't worry about that just yet. Canvas, for the most part, automatically grades most things. Oh, did we skip Unit 5? Sorry, I couldn't read what it said. No, Unit 5 was last week. It was temperature. It was very short. With labs, you're sending me a document, and I am manually grading those myself. And that takes time. I hope that when you are doing the labs, you aren't only taking about 3 minutes to do them. But it seems a little bit unfair for the student, I would say, that if you put an hour or 2 into the assignment, watching the video and answering the questions and maybe talking and collaborating with other students, that I grade your lab in 90 seconds and then hand it back to you. Like, I should probably spend more time, right? Well, if I do that, which I do, that means that it becomes a lot longer for me to get your labs returned to you. So, for instance, there are about 50 people enrolled in this class. If I spent 10 minutes on every person's lab, that would be 500 minutes of grading time, which is about 6.5 hours or so of just straight grading and reading labs. So the same thing over and over and over 50 times. I don't know how many of you have jobs where you do the exact same thing over and over and over and over and over and over and over again. Like exactly the same. Like maybe cut a circle out of paper over and over and over again. But it's super tedious, and you don't want to do all of that at once. So I break it up into chunks, and I do like a handful every day or so. And then the takeaway from all this is eventually I will get them back to you. I try to take about a week to do the lab grading and get it back to you. I did earlier mention that I was going to try and do it on Monday, but something came up yesterday, and I wasn't able to get any time to grade, so I still have about half of them left. So it's ongoing. Please do not email me about when you will get your labs back, because it doesn't help anybody. You get them back when I'm done with them. So I'll try to keep the turnaround not super long. So if you have any questions about that, let me know. All right, so that's all the administrative stuff out of the way. The next thing we're going to talk about are the things that are going to be on the screen here in just a second. So you can see that this is mentioning Unit 9. We're currently on Unit 6. We're going to do Unit 6 today. But at the time that we start Unit 9, you're going to be referencing some stuff known as polyatomic ions. So a polyatomic ion is a cluster of atoms that is stuck together. We're going to talk about all of these terms in just a second. But polyatomic means many atoms. So, for example, something like this could be many atoms stuck together. So, carbon and 3 oxygen. And then an ion has a charge. For example, that. And if I put these together, I get a polyatomic ion. I have a carbon and 3 oxygen atoms all stuck together with a total charge of -2 on it. And so the name of this, which you probably don't know just yet, this is carbonate. And I'm going to write the word ion after it just to let you know it's an ion. On the next page, I'm going to give you a list of polyatomic ions that you will need to have handy as a reference, or better, committed to memory. Because what's going to end up happening is later on in this course, and later on in other courses like 161 or Bio 211, or even some of your Orca classes, you're going to be talking about these ions a lot. And if you have to keep looking up what carbonate is every time you talk about ocean chemistry, you're going to get nowhere, because carbonate's super important. It's how CO2 is absorbed by the ocean. It turns into carbonate. Sorry, drinking some water there. So you're going to use them a lot. You'll want to memorize them eventually, but because it's an online class, we're not going to use them for a few weeks. Probably week 6 is when we're going to start seeing them a little bit, and then around week 7 or 8 is when they're going to come up a lot. So Unit 9, they'll start to appear. Unit 11, I'm going to expect that you know them, or at least have them handy. So be careful with them. Now, the list is rather large. And in fact, this is page 1. Here's page 2. So you could pause the video and look at this. You can see that all these charges here. So here's a charge. Here's a charge. Charges are always written after the substance. They are always written as a superscript. And all of the charges except for one are negative. This one over here is positive. So there's page 1. Again, you can pause the video and look at those. Here is page 2. And the little note on this slide is just that, hey, remember chlorate and all that stuff from this first page? That's these right here. And then these follow the same pattern as the ones that I bracketed. Does the lack of a charge mean that it is 1? So when there is a lack of a number, the number implied is 1. That's correct. Now, if there was no charge at all, it would be blank and its charge would be 0. So, for example, if I had C like this is carbon with no charge, but this would be carbon with a 4 plus charge. This would be carbon with a -1 charge, and so on. Anytime there should be a number, but there isn't one shown, it's implied to be 1. Now, in this case right here, there is no number implied at all because there's nothing there. Blank means no positive or negative. That's correct, yeah. We're going to talk about ions in more detail in Unit 7. Why is there a number on the top and the bottom? That's a good question. So this number right here, and let me get a different color here. This number that I'm going to put in blue, those are different numbers. The number on the bottom relates to the element in front of it. We're going to actually talk about this today. That's how many of those there are. So in this polyatomic ion right here, there are 4 oxygen atoms in it. How many chromium are there? Well, there's only 1 because we didn't put a number. And then in blue at the top, that's the overall charge. This is going to look kind of weird for now, but once we're done with Unit 6 and 7, we'll become more accustomed to what all of this means. And so your objective is, if you're going to start committing these to memory right now, is just look at them and remember that the name goes with a formula. So if you were to write acetate down, you should write C2H3O2 with a -1 charge. If you were going to write cyanide, you would write CN with a -1 charge. If you were going to write sulfite, you would write SO3 with a 2- charge, and so on. That's what I'm trying to get you to do here, is to try and learn these and commit them to memory. Do you have to memorize these? If this was an in-person class, my answer would be yes. But because it's an online class, I'm not going to come over to your house and like make sure that you don't have any reference materials. So, will you be able to have the list while taking a quiz if you have an in-person quiz in the future? No. At that point, we will expect that you have memorized these. So, if classes are in person in the winter quarter for you, which for the most part I don't believe that they are, but some of them might be. None of mine are. I've signed up for live stream again. We will have the expectation that you will have these memorized. Okay? So, this is for future you, but I realize that future you may have other things that they are working on, and that you may just want to reference this. And if you reference it enough, you eventually remember it, right? So, whatever gets you there. On this slide, I have some notes that talk about how to memorize groups of these at once. If you have anything that has 8 and 8 in it, 8 ending ions have 1 less oxygen than the 8 ions, so you might have noticed that nitrate and nitrite were very similar sounding. And they were only different by 1 oxygen. Well, anything that has ite is 1 less than its conjugate 8 form, we'll say. If you have hypoite, that's 2 less oxygen, and if you have per8, that's 1 more oxygen. So these are just patterns that show up in naming the ions so that you have less work to do. So if you can find bromate versus bromite, you know which one bromate is. You know all the rest of them because you can work from there. So work smarter, not harder. Or don't work at all. Print out the slide and have it handy when you need it. All right. So you're going to start seeing those in Unit 11 full time. We're going to mention them briefly in Unit 9. But today, our objective is to talk about matter. Why does matter matter? Matter's important because you and all of the stuff around you are made of matter. Our objective in this section, which we're going to do today, is to understand various states of matter that you'll encounter. In fact, there was a meme posted in the Discord chat about this already. And then we're going to try and categorize it the best that we can, because there's a lot of matter around us, and we're going to need to organize it in some sort of way that helps us identify its properties. Oh, excuse me. All right, so let's get started here. We're going to define matter as anything that meets these 2 criteria. Anything that occupies space and has mass. Now, if you're looking at these 3 things, 2 of them are pretty obvious. The statue of the orc, which I actually don't have on my desk anymore. He's been moved to the display case in the living room. I used to have him on my desk for this demo. I just point at him. Not that any of you could see that. But and then on the middle, I have coffee, which I'm not sure how many of you drink coffee. I don't personally. I don't really like hot beverages. Iced coffee, though, is awesome. I just don't want to make it. I have polar seltzer instead. Those are very obviously stuff-containing substances, right? You put the stuff in the cup, or you put the stuff in the mold and make the statue out of it, etc. But what about a gas? Are gases matter? Turns out that they totally are. There is something inside that balloon inflating it, right? And that's the helium. Or it could be hot air or any other gas that you put in there that would inflate the balloon. Is there truly a void or region where there is no matter? Turns out that the technical answer to that is yes. You could define a very small region in outer space where there are currently no hydrogen atoms or something like that. But the pragmatic or practical answer is no. No matter which cube size region you take, no matter where it is in the universe, you're probably going to find some matter in it. It's very difficult to find a place where there is absolutely nothing, although if you search small enough, you could find it. So matter is everywhere. We're going to look at 3 phases of matter, which I'm going to talk about in more detail on the next slide, and then we're going to draw some pictures. And you've probably heard of these phases before, solid, liquid, and gas, but these are not the only 3 phases that exist. They're just the ones that we're going to talk about. What about a vacuum chamber? That's a good question. A vacuum chamber is defined as a region that has a vacuum, right? A vacuum is just emptiness. However, even in a vacuum chamber, even the most optimal, perfect vacuum chamber that we can design won't remove absolutely everything. It'll try its hardest, but it will not get every single atom out of there. But that's a good prediction of something that'd be very close to that. What other phases are present? What about a plasma? What is a plasma? A plasma is just really, really, really hot gases to the point that they've been ionized. So in other words, their electrons have been ripped off of them. Where do we find plasmas? Plasmas are things like lightning. Fire is a plasma. The color that you see when you strike a match, or the color that you see of the flame when it's burning wood, or whatever, that orange or blue hue, depending on what medium you're burning. That is the plasma that exists. The sun is a plasma. Your TV might be a plasma, depending on how old it is. So it's ancient technology now, but in like late 2000s, plasma TVs were a thing, where you generate a plasma and get a color. Now everything is pretty much LED, because it's lighter. Seriously, I've had to move my plasma TV, and it's really freaking heavy. So plasmas are a phase that exists. We're not going to talk about them very much past that description. We're not going to talk about things like Bose-Einstein condensate, or supercritical fluids. Those exist, and we'll probably mention those in 162. But we're going to stick with the 3 basic phases because we're going to make this a very simple chemistry level experience for this course, and then general chemistry. Now, what exactly is chemistry? What are you going to be doing in this class? Chemistry is the study of how matter interacts with other matter, and what happens to it when it does that. So when you take 2 pieces of matter and you introduce them to each other, what happens? For instance, if I put a Mentos with Diet Coke, something happens. Is it Diet Coke or regular Coke that this works? I don't remember. One of them works and one of them doesn't. If I introduce those 2 things together, something happens. But if I do it to the other thing, it doesn't. If I put salt in water, what happens to the salt? What happens to the water? Do they change in some appreciable way? Well, the salt goes away, right? Why does it do that? That's what we're going to talk about in chemistry. If I make plastic and then sit on it, will my butt react with it? Hopefully the answer is no, which is the important part of, does the matter not transform? There are some instances we would like matter to not transform. For example, clothing. We would like our clothing to not dissolve on our flesh. So we choose matter that doesn't react with human skin, as opposed to, say, making your clothes out of hydrochloric acid, which would not be comfortable. It'd be rather itchy, it turns out. All right. We're going to define... Yeah, it would dissolve your flesh. That's where the itching comes from. Or soapy. We'll talk about how soap dissolves your flesh, which is the mechanism of cleaning, in 163, really. On the screen here, you could see illustrations of the different forms of matter that we have. And I'm going to zoom these in just a second. But what we're going to first define our phases by are these criterion: shape and volume. Shape is defined as a fixed region in space. So, for example, this would be the shape of my solid versus this being the shape of my liquid versus this being the shape of my gas. And so you could see that those objects have different shapes. They occupy a different region in space. So if I were drawing shapes, these shapes would be all different from each other. Obviously, because one's a rectangle, one's a circle, one's a triangle. But if I told you they all had the volume of 3 square centimeters, that's possible, right? I could draw shapes that all had the exact same area. Likewise, I could have different shapes that have the same volume. So these are independent properties of each other. I could have any shape I want to with any volume I want to. It just depends on the object and the phase. So volume is just going to be the amount of space that is occupied. We're going to typically measure volume in milliliters or cubic centimeters. And so we've got our shapes here. You could see that a solid right here, oops, I erased part of its shape. That's okay. Is going to be a fixed shape. Its shape cannot change or else it wouldn't be a solid, right? And you can observe that with many solids around you. If you apply enough force, yes, its shape will change. But if you apply a gentle amount of force, like you try and squeeze it with your fingers, like say your table is not going to change shape. It's rigid. Now, if something has a rigid shape, its volume cannot change either. So, by definition, a solid is something that has a fixed shape and volume. Now, what about a liquid? Liquids have fixed volumes. If I pour out 10 milliliters of water, I can put it in any container I want to, and it will still be 10 milliliters. But liquids occupy the shape of their container. But due to gravity, they are pulled towards the bottom of the container. Now, gases are subject to the same sort of thing here. However, they fill the container completely. Now, are gases subject to gravity? It turns out that over the scope of the entire atmosphere, they are. But because the individual particles are so far apart, gravity acts on each individual atom or molecule independently and has to exert a lot of effort over time to pull something down. In other words, this will make more sense when we draw the picture. Molecules that can move faster have a better chance to resist gravity. And we'll show that in a picture here, although when I was testing this earlier, my Photoshop was not doing great. So this might be an instance of, oh, Professor West needs to reboot his computer again. Oops, we don't want to zoom in way over there. I just didn't have time to reboot it before I realized, oh, crap. Alright, so I'm going to make a little region here. Alright, so there's my solid. Wow, we skipped 2 letters. My computer's just giving up on me. Huh? And then my gas, which I'm going to enclose here. Alright, what do the molecules look like inside each of these. In a solid, I'm probably going to draw these real slow, aren't I? Oh, this should be okay. Solids are jam-packed together, real tight, but they're very ordered. So I'm trying to draw these so that they're fitting in between the gaps between each atom. So we'll write that. Ordered, and regular. I hate Photoshop. I might just have to go and install something better. If I don't pick up my pen from the thing, it seems to work fine. But now, because they are ordered and regular, they are essentially stationary. Sorry, I'm trying to write without lifting my pen. And if the molecules are stationary, then they don't try and escape from each other, and they stay rigid. Now, in a liquid, your molecules are close together. Oh, it's just yelling at me that the encoder is overloaded. Okay. Yeah, it's just my computer being tired. Okay. In a liquid, my molecules have some freedom. They can go wherever they want to in the container. But they are still moving fairly slowly, relatively speaking. They move around and are in close contact with each other, but don't ever move far enough away to escape what we would call the shape or region that the liquid occupies. So we're going to say that these have some motion. There we go. Now, in a gas, the molecules are actually very far apart from each other. And they all move in independent directions. But because they are moving so quickly, they don't really have the ability to collect towards each other. Or one could say the opposite is true. Because they aren't collecting into a small cluster, they must be moving really, 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 really quickly. Because otherwise we could narrow them all down to one smaller region. Now, in a later course, we're going to talk about how all matter has forces that hold it together, kind of like how gravity attracts matter to the center of the Earth, or towards each other in general. There are other forces that have to do with charge that hold things together. And that's actually how we end up with these different phases. If things are held together really strongly, you get a solid. And if they're held together extremely weakly, you get a gas. We'll just say moves fast. That's good enough for now. So this is what our matter looks like at the atomic level. Solids are real dense and have lots of molecules packed in together in a very neat and ordered way. Liquids have some molecular motion, but the molecules are still in close proximity to each other. And then gases just move so quickly that the shape that they occupy is whatever shape they are constrained to. Whether it is a bottle that you've trapped them in, or the atmosphere itself. Now, with regards to gravity, if molecules are moving more slowly, then gravity has more of an impact on them. For example, if you throw a ball up into the air at like 5 meters a second, it will come back down. But if you launch it with a cannon at 500 meters a second, it will go much further and take much longer before it starts to return. Molecules move extremely fast. And so if you have independent tiny ones that are moving super, super quickly, and you have gravity acting in a downward pull on them, some molecules may get to the very edge of the atmosphere before they decide, you know what, it's time to go back. I don't know if I like it up here. And some molecules, like for example helium, just fly away and never come back. So that's how we're going to define our three phases. By the shape, by the volume they occupy, and also how they look at the atomic level. All right. There's going to be a picture of a guy on the moon here. We're going to talk about these terms. Volume is the space that matter occupies. That's the wrong command. I want this one. There we go. Helium flies away in large quantities, so like if you have it in a balloon, because it's less dense in there. So all of the helium together will, in a balloon, will cause the balloon to float up above the air, and then it would float on the top of the atmosphere. But individual helium atoms themselves are small enough to actually escape the Earth's gravitational pull. Whereas it turns out, like oxygen and nitrogen, not light enough to actually escape to an appreciable amount. You may read reports online that say, hey, the oxygen in the atmosphere is slowly escaping into space. Yeah, it absolutely is. So is every other gas in the atmosphere, slowly just disappearing. But the rate at which that's happening is extremely tiny. But for helium, if helium is released in the atmosphere, it's much harder to reclaim it because it is very easy for it to escape. All right. Feel free to ask me these random questions that are relevant, by the way. I don't mind stopping to talk about just random factoids because this is kind of dry stuff. Like, we're talking about what is volume. So if it keeps you engaged, that's great. All right, so volume is pretty straightforward. It's the space that stuff occupies. Now, the actual stuff in there is mass. And so all of the atoms and molecules and things like that that are contained in a region, that's our mass. That's what we're going to look at when we're dealing applications with things like kilograms or density or etc. Now, we're going to measure mass in grams or kilograms or the appropriate SI unit magnitude that we need for an application. So if we're working with something really tiny, we might use milligrams or micrograms. If we're using something really big, we might do kilograms or megagrams or whatever. But you've probably heard somebody is like jumping up and down above me in the apartment above me. You've probably heard these two terms and thought, well, maybe they're the same thing. And it turns out they totally aren't. On the left, we have mass, which we measure in kilograms. And on the right, we have weight, which pounds is actually a weight. If I asked you your mass, you could not say, oh, I weigh 210 pounds. Because that's not a mass, that's a weight. What's the difference between mass and weight? And the answer is, weight involves gravity. Gravity multiplied by the amount of mass is what we know as weight. In fact, if you've taken a physics course before, you've probably seen this equation. F equals ma, or force is the amount of mass you have times its acceleration. Well, in a gravitational field, m is the mass, and a is the acceleration due to gravity. And so this would be your weight. So your weight is just a function of how much matter is inside of you times the gravity of the celestial body that you are standing on. So if we go over here to the space dude, right here, or space dudette. Dude is kind of gender neutral now, isn't it? I mean, if you're from California like I am, it is. You'll notice that this dude's mass is 100 kilograms and his weight is 980 capital N. Capital N is what is known as the Newton. I wrote that on the wrong side. And again, if you've taken physics, you've heard of a Newton. A Newton is just a mass with an acceleration applied to it. The force is the amount that it would need to accelerate. Well, then, what's the mass unit for pound, then? If we know that kilograms and newtons are linked together, pounds must be linked to something too, right? And it turns out that it's a unit called a slug, which you may have heard about if you've taken an engineering class. The amount of matter that you have can be measured in slugs, but that, I guess, is odd sounding, so we Americans measure in pounds instead. Now, what if you go to somewhere where the gravitational constant is different? So here on Earth, gravity is 9.8 meters per second squared. But on the moon, it's much, 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 much less. I don't actually know the gravitational constant for the moon. I think it's like 2 meters per second squared. I'm trying to calculate by looking at this, but oh, it'd be 1.6. Duh. I just read the number right off the screen. So, the moon has less gravity, and as a result, you have less weight on the moon. But the amount of mass that you have is the same. I don't know how I got that really thin line there. So your matter is constant throughout the universe, no matter where you are, but your weight will change. The takeaway to this is that in this class, and in many science classes, if I ask you to determine the mass of something, guess what term we use for that? And that term is to weigh something. So, obviously, that's dumb. But unfortunately, that is just a sort of convention that scientists have adopted. If I ask you to get the weight of something, I am expecting you to return its mass. Okay? So be careful. All that to just get you to distinguish the two, and then what are we going to do? We're going to fuck around and use the wrong term, right? Thanks, 14th century scientists who made this. You guys suck. Now, if you want to call it getting something's mass, or if you want to go mass an object, that is also technically correct, and I would understand what you mean, but other students might not. So if you hear the word weigh in a science environment, the intent is, determine the mass in grams or kilograms. Okay? All right. Now, the thing about matter is you can't get rid of it. It's here, and it stays here. You cannot obliterate it and destroy it without extreme measures. And by extreme measures, I mean antimatter. Typical experiences that you are going to have on a day-to-day basis are not going to invoke antimatter. So, we're not going to study that. We're going to study much more common processes that occur. Chemical processes. In a chemical process, matter may transform. In a physical process, it will not. But in both cases, the matter remains constant. As in, whatever you put into the container to invoke the change, or no change, depending on physical or chemical, you're still going to have the same amount of matter in there. So, I have an example from the 161 textbook. This is the formation of beer. I'm not really sure what pre-beer is, but it's probably some sort of like watery mixture of yeast, maybe like additives for flavor, like spices or hops or whatever. And then you have some sort of food that your yeast will consume. Usually that's something like sugar. But you could use stuff like malt or brown sugar or whatever. The process that occurs is that the sugar... I lost my marker here. There we go. So the sugar reacts with the yeast. Actually, we'll write it this way. To make CO2 and other stuff. For example, one of those things that is made is ethanol. But other products are made too. So the yeast reacts with the sugar by consuming it. More appropriately, the enzymes within the sugar catalyze this reaction or facilitate it. And you end up with other stuff at the end. But if I were to put some number of grams of sugar in here, I should get X number of grams of stuff out. Now, that makes sense because I've got the bottle sealed, right? If I were to weigh this entire bottle here, we'll just say it weighs 274 grams. Before and after fermentation occurs, fermentation is the process by which beer is produced. I would find that afterward, the mass would be identical. And so this is called the law of conservation of mass. When you do chemistry, when you do chemistry in a closed container, before and after the chemical reaction, the amount of mass that is present will be constant. Now, the identity of the substances that are involved will be different, but the amount of matter that will be there will be the same. Now, you'll notice that I said a closed container. What if your container is open? For instance, my polar seltzer can. If I have a can of seltzer water and I have it closed and I weigh it on the balance, it will have some mass. This would be about like probably 380 grams or something, my guess on the weight of the aluminum. But once you open the can, and this is true of any soda, what happens to the can and its contents when you open the soda? What sound does it make? We'll draw a picture of it here. So here's my soda. Here's the liquid inside, and then here's all the carbonation. Which, Photoshop's going to love this. Yeah, encoding overloaded. I apologize if I drop any frames here, because my computer's really unhappy with it. So there's my CO2. And there's water and other stuff in there. But when I open the soda, you get a nice little fizz sound, don't you? And what that is CO2 escaping. Now, if it escapes, you can't weigh it anymore, yeah? So if you were to weigh a soda can and then open the soda can and then put it back on the balance, you could actually watch its mass decrease. Is it losing matter? Yeah, because the matter is escaping into the gas phase. So gases can escape, but the matter still exists. So we say that the mass is still conserved, despite the fact that we don't observe it using our tool anymore. So it's a matter of perspective, really. So let's apply this in a sort of practical way. I have Alka-Seltzer that I'm going to put into water. Alka-Seltzer is actually a mixture of two things: sodium bicarbonate and citric acid, or some sort of acid similar to that. I don't know if that's citric acid or ascorbic acid or whatever. But both of those things are soluble in water. They just aren't soluble in solid. And so your tablet doesn't react until you drop it into the water. Then it starts to dissolve because the two substances react and form CO2. The CO2 that is formed escapes from the container. There it goes. And so we do an experiment with the following things. I put 10 grams of Alka-Seltzer tablets into a glass with 50 grams of water. So I know that before I have reacted anything, the total mass is 60 grams. I weighed them independently. Then I add them together, and it starts bubbling and fizzing. And when it's completely done bubbling and fizzing, I weigh the entire thing, and the water in solution, including the stuff that is dissolved, has this mass, 57.9 grams. So my question for you is, what mass of carbon dioxide must have been produced in the reaction, assuming the conservation of mass is true, which it is? So how many grams of CO2 do you think were released into the atmosphere here? Go ahead and give your answer in the chat, and make sure you give it to the right number of sig figs. There you go, very good. 2.1. Now, how did you get that number? Hopefully, you got the number 2.1 by just doing subtraction. 60 minus 57.9, right? And since both of these numbers go to the 10th place, your answer should also go to the 10th place too. So there's my 10th place, there's my 10th place, there's my 10th place. Very good. So the conservation of mass is actually a really important property in the laboratory to remember, because you can immediately tell if a reaction has gone appropriately or if something has screwed up by doing a conservation of mass check. So if your container is closed and you started with 50 grams and you ended with 38, maybe your container wasn't as closed as you thought it was. Maybe you have a leak in there. And so that could be a good way to debug or diagnose things. All right. We're about ready to take our break here. I'm going to take the break a little bit early here because we're going to start a topic that I won't be able to finish in 10 minutes, I don't think. So let me get the break card up on the screen here. We do need the timer. Will it capture the timer? Oh, will. Look at that. Okay. Do you want to update this timer? No, never update anything. That's not true, but in this case, it is. All right, we'll get some more music up, and we'll see you in just a bit. All right, we're back. And wind the music down here real quick. All right, I hope you enjoyed Donkey Kong Country, a game I played in 1994 when I was 11. I was very good at it, it turns out. Not so much nowadays. there is evidence on the internet to sort of prove that. Although I did win the race that we played Donkey Kong Country 2 in. We'll have music from that tomorrow, and it's even better than the original. All right, let's talk about some things that you can do to matter. So the first set of interactions that we're going to talk about for matter are just going to be actions that we can take on it in the most broad sense. So, for example, if I had like a piece of aluminum foil, we'll say that the aluminum foil is my matter. I could fold it in half. That'd be something I could do to it. Or I could tear it into pieces. Or I could drop it in water or hydrochloric acid. Or I could light it on fire. Or I could bake with it. Or I could crunch it up into a ball and then the cat will bat it around. These are all things that I can do to the foil. Now, what we're going to need to do is find some sort of way to categorize it. And this is what we're going to use as our rubric. We're going to look at actions that change the identity of the matter and other actions that don't. For instance, in my aluminum foil example, crumpling it into a ball and giving it to the cat to play with is not an action that would change the foil. It's still foil, right? If I really absolutely had to, I could uncrumple it, flatten it out, and use it for baking. Probably shouldn't, but you could. However, if you dissolve the aluminum foil in hydrochloric acid, that's not going to be recoverable, right? If I burn it, like I combust it on fire, not going to have aluminum at the end anymore. I'm going to have something different. Does aluminum foil burn? It does under certain circumstances. It turns out. So some of those actions can be recovering the aluminum foil. Others can't. You could replace aluminum foil with any other substance in this context, and in some cases you'll be able to recover the object. In other cases you won't because it's been irrevocably reversed. We're going to use that as our rubric, okay? Oh, shoot, I keep pushing buttons and it's not moving my slides forward. There we go. All right, we're going to subjugate these ideas into both properties and changes. So, not subjugate, subdivide. What am I saying? So, we're going to subdivide all of those things that we just talked about into either being a property or a change. Most of the things that I talked about on the previous slide were changes, but we can also assess properties of an object too. For instance, if I look at water, I could say, oh, water is a liquid if I have it at room temperature. Now, me noting that doesn't change the fact that it's water. If I taste chocolate, it tastes sweet. It's still chocolate, at least whatever's left there. I'm not actually doing something that changes it. So these are all properties. Properties are traits that objects have. If you are just looking at the properties of something and you don't change it, that's going to be different than doing some sort of action that does cause it to change. And that would be these things right here. For example, if you have a solid ice cube and you leave it out on the counter, it'll turn into a liquid. It'll melt after a while, right? If you have bread or bagels or something bread-related and you put it in the fridge, it'll last a long time, but eventually it gets moldy. If you leave it out on the counter, it gets moldy much more quickly. If you have something made of iron or steel, and you scratch it, then what ends up happening is that eventually, as water interacts with it, it causes corrosion and rust. These are all changes that are very, very difficult to reverse. And as a result of that, we're going to categorize them as something different than just, oh, I looked at it, it's purple, which doesn't change the identity of the substance at all. So with those two categories in mind, things that are properties and things that are changes, we're going to look at various actions. Oh, excuse me. We're going to look at various actions and determine whether what is going on changes the matter or does not. And the algorithm that we're going to use is, for any given action, we're going to look at the chemical formula before we do the reaction, or action, I should say, and then after the action. Now, what is a chemical formula? Well, this is an introductory chemistry class, so you've probably only seen a few of these before. Everybody's heard of H2O. Everybody's heard of O2 or CO2. A chemical formula is just whatever the composition is, written as a formula. For many molecules, it's simple to write that. But for several categories of matter, for example, like protein or carbohydrates or cell walls or things like that, it becomes very difficult to write the formula. So we're going to use a generic one. Now, even though we can't necessarily write the chemical formula for, say, paper, you can imagine that some such formula exists. What we're going to do is yawn. Oh, sorry, hold on. I didn't get much sleep last night. What we're going to do is we're going to try and envision or imagine the formula of our substance before we do an action, and we're going to try and envision it afterward. And what we're going to do is we're going to look for whether the formula is the same or different. Now, again, you might not know the formula, so you'll have to make an educated guess, but there will be a lot of opportunities for you to develop the intuition that's needed for something reasonable. And we'll go over that as we go through this section. So our first example here is if something does not change the formula, we're going to call that physics, or a physical property or change. So in our aluminum foil example, this would be me tearing the aluminum into small pieces, or me folding it into an origami crane because it's shinier, I guess, that way. I don't know, it seems kind of cool. Or crumpling it in a ball for the cat. It's still aluminum, right? The formula for aluminum is just aluminum. Al. So before and after those actions, before it's just a sheet of aluminum foil. Its formula is aluminum. Afterward, it's still aluminum. So what we did was physics. What sorts of actions are physical properties? General observations that just note traits about an object, by definition, can't change the formula of matter. If I look at the can of seltzer water and I note that the label is purple, my act of perceiving the can does not change its chemical formula. Likewise, if I turn on the faucet and I put my hand in the water and go, "Ah, that's hot," me noting the temperature of the water does not change the fact that it's water. So anything that's a general observation, like you can determine this by either looking at it or measuring it with some sort of tool, is going to be a physical property. Now, what about a change? Ooh, that was a lot darker than I expected. That's okay. What about a change in state? For example, if I have ice and I let it melt, ice is frozen water, right? Its chemical formula is H2O. When the water when the ice melts into water, its formula is still H2O. Now, a good way to understand, oh, is this a physical change in reality? Like, maybe you don't know the formula of something and you aren't sure it's a phase change. Can you change it back? And the answer is, well, if I could write this. There we go. So if you melt something, that would be a physical change because it was a phase change. So melting changes the phase of something from solid to liquid. Now, if you aren't sure if something is melting, try to revert it. Try to freeze it. What's the opposite of melting something? Freezing it. Can you make water turn back into ice? You can if you put it in the freezer. Typically speaking, physical changes are very easy to reverse. For instance, if you crumple up your aluminum foil into a ball, you could uncrumple it. It's not very hard. You just pull it apart and then make it a sheet again. It'll have a bunch of folds and creases in it, but it's back to its normal form as a sheet, and you could use it as such. If you have a piece of paper and you tear it, can you revert it back to normal paper? Yeah, you can. You just tape it. Tape it on the other side that you don't want to write on, and it'll function like a piece of paper, right? Now, you can't rebond all the chemical bonds that you tore, but overall, it's still paper, right? So we show that on this next page here. Now, you have to use common sense to the best of your ability, or just your intuition and judgment in some of these cases. So, for instance, if I don't know the formula for paper, I can at least note that before and after I tear it, it's still paper. So, taking those sorts of actions that manipulate the object but don't necessarily transform it are examples of physical actions that you can take. So those are the two big ones to look out for. Is it physics that you're doing? One, is it a phase change? Are you going from solid to liquid to gas? Or backward? If so, what you're doing is physics. Two, are you just manipulating the matter in some way? Are you pouring it into another container? Are you smashing it into a different shape? Are you tugging it until it's two pieces? Are you bending it until it's a straight line? Those are all examples of things where you change its shape, but not its identity. Okay? So be careful of what a given problem is trying to ask you, and you'll be able to identify, oh, this is probably a physical transformation or change or observation that is going on. All right, so that's the physics part of this. If the formula doesn't change, it's a physical process. Now, what if the formula does change? For example, if I try to burn paper, if you take a matchbook and you strike a match and hold it up to a sheet of paper, the paper goes up in flames, and you get like this sooty brown ash, or gray ash, that chars up. It's very, very flaky. And it's very, very different than what you started with. Now, again, this is kind of difficult to predict. You don't know what the formula is for paper. And you may not know what the formula is for ashes. I do, so I wrote it on the screen here. You make carbon dioxide when you burn stuff. And ash is just carbon or various forms of it. Now, if you don't know that the formula is changing, what you can do is you can observe the properties of the substance before and after. And usually this works. Now, phase changes sort of screw this up a little bit, but you can always ask yourself if you can do the reaction in the reverse direction. For chemical changes, it's extraordinarily difficult to reverse this. How do I turn ashes back into paper? Well, pragmatically speaking, we would have to do something along the lines of bury the ashes in a region where a tree was, plant the seeds for a tree, let it grow up into an adult plant, cut the tree down, and then take the timber to the lumber mill to have it processed into paper, and then you can get the paper back. So you could, in theory, do it. It would take a lot of time and effort, though, and so not very practical. Not something you could just be like, oh, let's just do this in reverse. So chemical changes are exceptionally difficult to reverse most of the time. Almost universally, these reactions go in one direction. What we're going to learn later on in 163 is that all reactions proceed in both directions, just one direction primarily. And for the reactions that are hard to reverse, there's a reason for that. So using that as your rubric there, can you undo it or not, is actually a really good starting point. It's not the entire picture, because can you undo it? The answer is technically, yeah, you can undo anything. So it falls apart, but it's whether can you undo it easily? And that's relative, of course. But is it relatively easy to get ashes back into paper? No, that's not relatively easy. Is it easy to unfold the paper? Yes. So you could tell one of those is much easier than the other. So the easier one is most likely to be physical. And in this case it is. And in most cases that will work for you. Now, I'm just sort of trying to give you a bunch of tools to help you do these sorts of analyses, because I'm going to give you a bunch of problems in a second, and you're going to look at them and say, oh, okay, is it a phase change? Well, maybe you're not sure. So what do you fall back on? Well, if you do this, can you undo it easily? And if the answer is yes, it's probably physical. And if the answer is no, it's probably chemical. The other thing that you want to look at is look at formulas. If the formula changes, it's always a chemical reaction. And then, lastly, if you weren't sure, how do you use the new matter? Do you use it for the same purposes? Now, again, that'll be kind of general. Ice and water aren't necessarily used for the same purposes, but they are used for similar purposes. You consume both of them. In paper's case, if you try to write on paper or fold paper or do something with paper, turns out you can't really do any of those things with ashes. And so they're different enough that you can say, okay, chemistry must have occurred here. Okay, so that's what our rubric is going to be. Try to use those guidelines to determine whether physical changes or chemical changes have occurred for a given scenario that I provide to you. Now, it's not going to be a perfect guide, but the examples that I give you or ask you to do should fall into one category or the other based on the ground rules that I've set up for you. So if there's a phase change, physics. If there is a formula change, chemistry. If it's easy to reverse, physics. If it's difficult to reverse, chemistry. That sort of stuff, okay? All right. Now, because this is a chemistry course, we're going to focus on chemistry for the most part, right? Here's the burning of aluminum shown in an equation here. So I started with aluminum. This is our aluminum foil. If I combust it in the presence of oxygen, I get aluminum oxide. This is a protective coating. That's actually sprayed on the inside of aluminum cans so they don't corrode. Because the acidity of certain beverages could cause aluminum to dissolve slowly over time. So we protect it with a coating of aluminum oxide. Now, aluminum oxide is not as corroding as aluminum is. Aluminum will corrode over time when exposed to acids. All right, so we're going to look at various examples here. And what I want you to do is in the chat, I want you to assign either chemical or physical to each of the following observations. Now, some of these are state changes. Some of these are like I'm burning it. Some of these are I'm just looking at it, etc. And so what I want you to do is either you can number them, I guess. We'll do 1, 2, 3, 4. We'll just number them down here. And I want you to tell me physical or chemical? Okay, so P or C. I'm going to give you 5 minutes to go over these in the chat with each other. Talk it out with other classmates, and once we're done, we'll go over the answers. Okay, see you in a bit. Say hi. Say hello. Say hello. Two more minutes and we'll go over the answers. All right, let's go over the answers here. I gotta find the stylus, though. There it is. I always put it in the same spot, except when I don't. And it's those times where it's like, oh crap, where the heck is it? All right. Now, in each of these, there are a few words that are going to point out what it is that's going on and that you should pay attention to. For example, we don't care about make delicious pasta. You could just rub that right out. It's gone. But what we do care about is water is boiled. Well, when you boil water, what happens to it? It becomes steam, right? Now, can you turn steam back into water? You usually don't, but you can. And in fact, a place that this often happens is if you're using your shower, the steam that is produced in the shower, when it hits the mirror in the bathroom, it will cause the water to condense. And then it becomes water droplets, and those water droplets then fall down. So this is a reversible process. Boiling and condensation are the opposite processes. So water boiling is just a phase change. And we said that anything that is a phase change is a physical transformation. So we're going to label that. For the second one, we observe something to be purple. Now, if I observe that it's purple, my act of looking at it and perceiving it does not cause it to change in any way. Not unless I have, like, Superman crazy X-ray eyes or something, which, in that case, see your doctor. But for the rest of us, looking at something is just our eyes receiving visible light that is either refracted or reflected off of something. Or through it. As a result, that's also a physical process. Now, this third one contains a word that I don't like to use for figuring out whether it's physical or chemical. And that word is dissolved. I'm not going to highlight the word dissolved here. And the reason for that is because if something dissolves, it's a little ambiguous because you might be able to recover it. For instance, if I have some tap water and I put sodium chloride, table salt, into it, and I dissolve it, it would go away, right? But I could get the salt back by boiling away the water. I could just heat up the water until it starts to boil, and what will be left in the bottom of the glass would be the salt. However, if I do this example with the Alka-Seltzer and dissolve it in water, it ends up being a different process entirely, and I actually can't get the Alka-Seltzer back once it's dissolved. And the reason for that is because of this part. This is the actual relevant part to our discussion here. Does water normally release gas? I hope not. Otherwise, what you're drinking isn't water. Does Alka-Seltzer on its own release a gas? Well, if it did, the box you buy it in would be kind of like expanded, right? It would have a packet of gas in it. So clearly it doesn't do that. It's the act of putting them together that causes the gas to be released. So the conclusion that we would draw is that, oh, chemistry must be occurring. Typically, things that release gas, good indication that that's chemistry going on. All right. What about melting something? We talked about earlier that melting is a phase change. Now, it doesn't matter that it's something that you don't recognize. It's still a phase change. Sodium metal can be melted just like any other metal can be melted. All right. This next one right here, if you ignite something, can you unignite it? Or can you just ignite it a second time? Typically speaking, no. You can't burn your wood twice. You can't light a match twice. You can't fire the gunpowder in a bullet twice. All of those things require a combustion reaction, which only goes one time. You're reacting with oxygen to form new products, as well as energy. But you can't undo that easily. So this must be chemistry. For number 6, we got air in a scuba tank. How did it get there? Well, we just pushed it in there, right? Now, if we put air into a scuba tank at the same pressure as it was out here, how long do you think it would take for you to go through the air in a scuba tank? Probably about a minute, right? Because if you take a deep breath, that amount of air that you expand, your lungs expand and contract, is roughly 2 liters or so. 2 to 4 liters, I think, something like that. A scuba tank is probably only about 20 to 30 liters, so you'd be good for about 20 breaths. You'd last about a minute with that amount of air. That's clearly not enough air. So what we do is we compress it. We put more air by making more air take up a smaller volume. But it's still air at the end of the day. So when the air is compressed, all we're doing, there we go, is changing its shape. If you open the valve on the scuba tank, the air will come right back out, and it will be how it was before. So that is an easily reversible process. So it must be physical. Now, number 7 I include because this is one of those cases where can you turn it back to how it was fails, but it still ends up being physical. We'll just write that down because that's the answer. So you have to be kind of careful. There is no one golden rubric here. But the chemical formula changing before and after is the definition. And you can tell by, oh, if I cut a piece of wood down into a smaller chunk, it's still wood, and therefore would have the same chemical formula. And therefore, whittling lumber must be physical. Now, could you put it back together? It'd be extremely tedious, and it would probably fail the, oh, this is easy to do test. Like, if my great aunt was she used to do woodworking, and she would sculpt all these like little animals out of wood. And the amount of detail that goes into some of those things, to get it back to being just a piece of wood, would take a lot of effort, actually. And so our description of can you reverse it easily falls apart here. So it's, again, all of these that I've given you are not foolproof, and there will be some leeway in like, is this easy to do? The formula being the same before and after is the definition of this process. But it's not always the thing that we can use, so use your best judgment. I clicked on the wrong thing. Sorry. I want this one. That's what I want. So I would highlight this as the thing that tells me, oh, it's physical. And then down here, oh, this slide makes me nostalgic. Back when I used to have a motorcycle. Gasoline is combusted. When you combust things, you get carbon dioxide and H2O and other products, usually. But you don't get gasoline back. You don't capture the exhaust from the combustion of your gasoline and get to reuse it. So, we must be doing chemistry here. Gasoline cannot be reused. You get to use it one time. Alright, so there you go. Physical versus chemical. Any questions, let me know. Alright. For this next section here, this will be a little brief section on labeling stuff with one of these two terms here. If I give you an amount of stuff, and I said, which of you has the bigger volume? You could easily determine that, for example. Like if I gave half the class 1 liter of water, and I gave the other half of the class 10 liters of water, and I said, who got more water? That'd be obvious. The side of the class that got 10 liters of water. If I asked you, whose water has the largest volume? That'd be easy to tell because there's 10 liters, right? Who has the highest mass? Again, easy to tell. Highest weight? Easy to tell. Okay, whose water has the highest boiling temperature? Oh, well, suddenly the amount that I gave you doesn't matter, right? Some properties do depend on how much you have. Other properties don't depend on that. Whose water is the most dense? If you poured all the water into a trough, would one side of the classroom's water float to the top because it's less dense? No, it's all water, right? Everyone's water is the same density. So we can categorize properties based on whether it matters how much you have or not. We're going to use the term extensive to describe a term or property that does depend on the quantity of matter, whereas an intensive property does not depend on it. So something like weight or mass would be extensive, whereas color would be intensive. If I give you 1 liter of Kool-Aid versus 100 liters of Kool-Aid, and the Kool-Aid is the same concentration, they'll be the same color. The color doesn't matter, or the volume doesn't matter for the color. All right. So I'm going to give you a bunch of these, and I want you to tell me, to the best of your ability, which of these are extensive and which are intensive. And the rubric, again, is if I give you more of it, does this property change? If it does change, then it's extensive. If it does not change, then it's intensive. Okay? Tell me extensive or intensive for each of these. I'll number them again for you so that you can put your answers in the chat. And I'll give you about 2 or 3 minutes to do that, and we'll go over the answers together in just a second. One more minute. We'll go over the answers then. All right, let's go over these. So again, our rubric is, if I give you more of it, does the property change? So first, let's look at volume. If I give you more stuff, its volume must increase too, right? So volume must be extensive. Oh, I'm hiding the chat. It fell behind the screen here. There we go. All right, what about flammability, though? If I give you more gasoline, does the gas become more flammable, or is it the same flammable? Well, gasoline on its own is flammable. Doesn't matter if I give you 1 milliliter of it or 100 milliliters of it. It'll burn just as easily. So this is intensive. Now, you could actually go a bit further and say, well, if you have too much of it, it won't combust. You need the right amount of oxygen. But we're assuming the right amount of oxygen for this problem anyway, when we talk about flammability. How about boiling point? If I give you more water, it takes more heat and more energy to boil something, but the temperature at which it boils would be the same. And so this is intensive too. Mass, I think we can just say that that's extensive without any discussion there, because that's sort of the definition. This last one's a little bit interesting, though. If I give you more stuff, would the state change? And in almost all cases, the answer to that would be no, right? The state would be the same. So the intent here is that state is intensive. However, there are some edge cases where if you put a ton of gaseous something into a small container, eventually it would liquefy. That is something that can happen, but we are changing a lot of variables when we do that. I'm just talking about out in the atmosphere, out in the open here, sort of stuff. For some reason, half of my extensive disappeared. Oh well. I think my computer is just... it wants to die. This is how my computer feels right now. So I might have to go give it a break. We're going to call it a day here because the next section is longer than 10 minutes, has examples, and I want you to do them rather than me get to the examples and then stop. So that's where we're going to end today. I do want to thank everybody for coming out to the lecture. Tomorrow's lecture, we will finish up Unit 6. We'll move on to Unit 7. Once Unit 6 has been finished, there will be a quiz posted. So that'll be quiz number 3. It'll be Units 4, 5, and 6. And you will see that online tomorrow. I'm going to go and try and get some of the labs graded. I think I'm going to work on that right now. Once I reboot my computer, of course. But other than that, that's pretty much it for me. Have a wonderful day. And I'll catch you tomorrow. Make sure you let me know if you have any questions in the Discord or email. And make sure to get quiz 2 in by tomorrow. Closes Wednesday. Have a good one.